it's cutting it in half a certain way. And that means we cut it in half. See, we're cutting it in half with a right angle. See that right angle? That's a perpendicular bisector. So now the question arises, how the heck do you do that? And I'll show you a short video, and the video is less than 10 seconds. And then I will give you the link to the video in the Blackboard information where I put all the solutions and all the random stuff I show you during class. But I'll show you a video. It's better than me drawing it. Anyway, you extend the compass more than halfway, and then you trace out a circular arc. Now, in this case, notice that they don't trace out the full arc. They just trace out a couple of the arc pieces here, but not the full arc. That's okay. The main thing is that this compass has to extend more than halfway. Now go on the other side and do the same thing. And what you're going to do there, due to symmetry, is once you connect this point with this point where they intersect, get your straight edge, there you go. That's how you do it. So let's run it again. I'll play it a couple more times for you to see. Go more than halfway. Extend that arc. And repeat. Now, if back in ancient times, you're probably guessing that they didn't walk around with geometry sets. And you'd be right. They don't walk around with geometry sets. However, all you really need to do that construction, let's say that we were at the beach. How unrealistic right now with the weather outside. But let's say we were at the beach together, and I gave everybody, I put you in groups of like 4, and I gave you some string, and maybe a lot of string, and maybe a couple of sticks. And just with those things, you could actually do that construction in the sand. Do you kind of see what I'm saying there? Would that be something that you could do in the sand? You could construct it? Who thinks they could do it in the sand with some string and a little bit of maybe a couple of sticks or something? Isn't that cool, Tommaso? You could totally do that. And it's amazing because what do you think they did back then? When they were surveying and plotting out lands and they needed to cut out line segments in half, they were able to do it in such a well-done precision because it doesn't matter the instrument having readings on it. You don't need to know centimeters and inches on this ruler. Yeah, they made if they were playing the game Survivor, like that TV show, they would ruin us compared to today. Now, what does this thing offer us? It offers us 2 key things. The first thing that this shape or this construction, we want to call it a construction. The first thing this construction offers us is this guy right here. Can someone tell me what the green dot here is? What would be the geometric name for that green dot? That green point? Yeah, just use a different word there, but you're on the right track. Midpoint. Midpoint. It's the intersection point of the perpendicular line and the original line segment. But the key thing is that it's a midpoint. It also offers us, of course, the right angle. So those 2 things are very, very powerful. And I'll demonstrate to you. I'm going to try to draw this freehand, so it won't be perfect, everybody. But I will show you the following construction, and I think you'll be amazed. Here's the challenge. Let me just get the figure nice. Okay, here's a triangle. Imagine right now we were in ancient, let's say in ancient Greece or something like that. And you as a construction manager or as a technician or as an engineer or whatever the heck your role was back then, you were tasked to do the following: to draw a circle, but to only touch these points on this triangle. Isn't that the worst circle of all time? How bad? On a scale of 1 to 10, 10 being amazing and 1 being get a new job, what would you rank my circle here? Give me a grade. Amira, you're so positive. I love it. Yeah, I'd give myself a negative. Jeez. 0.5? Malik, take it easy, buddy. You guys are ruining me here. Show some dignity. Damn, that was for me, not for you. Okay, so watch. I got fired. I totally just got roasted by a bunch of students. I love it. Okay, now let me show you that with some very intelligent artistry, I can do a better job than what I just did. Okay. Now keep in mind that I'm going to be a little bit of a baby and say that it's not my fault. It's because my computer's glitching, and I won't lie to you. The computer does have a delay. I told you you're gonna have fun today. Now, here's my line segment. I'm gonna do this thing that we did on the previous page. Remember this process? I'm gonna get the perpendicular bisector. So let's do that here. So imagine I went through that process here, you know, the video I just played for you, and I did this. Okay. I'm just gonna try to guess it. That's okay. I think that's all right. That's actually garbage. Never mind. Your buddy here, Johnny, is gonna do a good job. Otherwise, he's not leaving here with his dignity. What do you think? Is that good enough, people? Who thinks that's okay? I don't want to get my geometry set on my computer screen right now. But do you feel that's okay? Is that like sufficiently decent? Let me know. Do you think I should move it a bit? Okay. I got approval. All right. I'm not looking for a high five. I'm just want to make sure it doesn't look like crap. That's all. Okay, let's do another one here. I think it's a little bit off the true there. What do you think there? I think it's good there. That's okay. I'm going to say that's okay. So, all right. I'll use pink again. So this time, notice here. Tell me if this is right. Is this correct in the chat? Should I do this? Shoot. Should I do this? Tell me what's wrong with this. What's wrong with my labeling? Yeah, what's wrong with it? Tell me what's wrong with it. So the mistake here is that I can't label it with a double because this is a double. Why are they equal? Do you mean these two, Amira? Why are these two equal, or why are these two equal? It's because of the previous thing. I'm doing the perpendicular bisector. So perpendicular bisector, I'm cutting it in half. By this construction, I'm cutting it in half. So these guys are deliberately being cut in half because I'm using that particular geometric construction. Is that okay? All right. So here's the awesome part, people. You could do the third one as well. You could do this one as well, but you don't need to. It's redundant. So I'm not going to do the third one. If you don't mind, I'm just going to skip that because you don't have to do it. It provides you a good check, though. But anyway, the perpendicular bisectors, these guys here, where are they going to meet? They're going to meet right here, and that is the center of the circle. That's the center of the circle. How amazing is that? Honestly. How amazing is that? Or maybe I'm too excited about meaningless things. Nobody is amazed. It's so sad. Okay. All right, so obviously I'm going to lose my I'm going to lose the image here, but if you were to draw a circle, I don't know how to make it transparent. There is a way to do it on the side somehow. Anyway, I'm not going to do that. I'm just going to freehand it, if you don't mind, because that's not looking very promising right now. This is very painful, everybody. I'm sorry. All right, anyway, You get the point. I give up on that. I wasted enough of your time already. Okay, I'll just leave it at that because I'm not really doing a good job of drawing the circle, and we should move on. Anyway.
We got the picture on that for sure.
Thank you. Okay, here's another one. Centroid. You can use the construction I just showed you to find out where the centroid of the triangle is. Now, what does centroid mean? So centroid is the geometric center. If this object, so if this thing was made of the same material, let's say this was a piece of sheet metal. This triangle here was a piece of sheet metal, and you wanted to figure out where the center of mass is for it, then you could use this. You could use the perpendicular bisector to achieve this goal. So I'm going to do what I did on the previous page to this page as well. So here's my previous drawing. So let's do that here. And we're going to see that you could find the centroid of this triangle with the same construction. So I did the perpendicular bisectors, but the centroid is done a little bit different, people. What you do here this time is you use the midpoint. See this midpoint here? And you use this midpoint here. And using a different argument from geometry, you can connect the midpoints to the other corners of the triangle. And that would be, for example, from here to here, let's say. Don't worry, I'll just color that in a second. I'll give it a nice dark purple or something. So where those two line segments or medians intersect is called the centroid. So this is the centroid right here. Centroid is this thing right here. How is this useful in construction? Well, let's say this thing here, let's say this overall shape here, let's say that it was a very heavy and complicated, complex component on a construction site that you had to lift by crane. Imagine that this thing here was like 4 tons and that a crane operator had to deliver this to the top of a structure. Now, if you're going to lift this thing by crane or by any device as such, you want to make sure that wherever you anchor it, wherever the junction is, like if there's, imagine there's cables, right? There's cables pulling it up. These are cables, or wherever the cables are attached. You really want to make sure that the cables connect each other or intersect each other as directly above this centroid as possible, because that would offer you the safest delivery mechanism to the top. That's right, you got to have that stability. Now, let's say that you're on a construction site and that there is a structure, a piece like this. You do not need some fancy equipment, some high-tech gadgets to find the centroid of it. You literally could be on the construction site with some string and a marker. And you could in less than 5 minutes with a string and a marker, you could get a very, very quick estimate of where the centroid is. Now, you probably want to do this whole bisector thing, because all you really need is the midpoint. So on a construction site, what you would do is probably just measure this with tape measure, and then find the midpoint and connect the two midpoints. But in any case, if you wanted it to be, if you wanted to use the skill which I showed you, which was the perpendicular bisector, then you could totally do that as well. So anyway, what have I shown you so far? I've shown you perpendicular bisector, and I've shown you one application here, which is this, a second application, which is this, and now I'm going to show you a different construction, something else, and it's called the angle bisector. So this one here, people probably remember it from like, they might remember it from middle school or something. Who remembers angle bisector from middle school? Who knows? Anyway, What an angle bisector is, there's two words there. Angle, you know what an angle is. This is the angle. And bisector is a straight line that cuts something in half. I really should have mentioned that there, okay? I mean, you can get more fancy definitions. Bisector, a line that cuts something in half. So that's like, this is not a professional definition from a geometry book, but it is a very solid way of saying it in 2 seconds to somebody and not being too fancy about it. A line that cuts something in half. So in the previous situation, it was a line that cuts another line segment in half, and perpendicular meant at 90 degrees. Now we have this thing here, which is a line. We want to draw a line here. So here's our original angle. We want to draw a line here so that we cut this angle in half. So that's what we're trying to do here. So how do we do it? Well, I'll show you a video for that as well, and I'll put the two videos on Blackboard at the end of class. Anyway, here we go. Take your compass and do this and do that. So that's part one. Part one, you got to make sure that the compass, it has the same radius for both values. Now what you're going to do is you're going to move the compass. You could change the compass, you could change how much the compass is here, like if you don't have space on the page. Or you can just keep the compass at the same setting all the way through. Get your straight edge and do that. I'll stop talking, I'll play it 2 more times. Again, last time, take your compass, pick a position, and you can try this. If you have a geometry set at home, try it. And then you do that again 1 more time. And get your straight edge and you're done. So that's how you cut an angle in half using the construction of an angle bisector. So just for this diagram here, I'll complete the figure. I don't want to get the geometry set out right now on the screen here. Good enough. So these are the same. Now, what can you use this for? Do you remember earlier we drew a circle around a triangle? We call that a circumscribed circle. Now what we're going to do is we're going to try to fit a circle inside the triangle. So that's called an inscribed circle. See, inscribed a circle. So what you want to do here now is you want to use the angle bisector, and I'll just follow the recipe here. I've actually written the recipe for you up here. That's right, it is inscribed, yes. You want to follow the recipe here of what I've said here. So let's do that here. I'm going to get my, I'll use the PowerPoint geometry shapes here. So what you do is you cut this angle in half. Now, just to the best of my knowledge, I think that's halfway. Hopefully it looks good enough to you. But you can use the skill I just showed you. And you can do it again 1 more time. Does that look good? Is A cut in half there? What do you think? I'm not going to put a protractor on my screen. I don't want to embarrass myself too much, everybody. Anyway, it would be nice to do this in class on the board with you because it is a lot of fun, and students tend to, you know, I get them to get up there with me and kind of like help me draw it on the board. Anyway, this point here, where the angle bisectors meet, this point here is the center of the circle. That's the center of the circle. So what you do now is you can get your compass and kind of trace it out like that. And obviously this is not like pro level, but it is just something that I'm doing freehand with you on a very glitchy learning platform. Good enough. Honestly, I think that's respectable. This is a little bit of a mess here, but it is a respectable drawing. So, oh, that's amazing. That's amazing. Now, do you guys remember in the second class when I talked about those 7 basic rules? Remember the 7 rules? This is actually one of the rules. This is actually one of those rules. If you take a circle and you do this, and you draw a third line segment that goes through the center, it cuts the angle in half. It's the tangent rule. Yes, thank you, Shalon. This is rule, I think it was rule number 6 or 7, but don't quote me on it. I'll put 6, 7 question mark. Oh, number 6. Thank you so much. And I mentioned to you back then, I go, I don't number the rules. I don't remember the numbering because the numbering is arbitrary. I could have named the rules my favorite animals, zebra, whatever, okay? So anyway, now the cool thing is that you have this booklet with you. Whoops. You have this booklet available on Blackboard, and you can actually, if you want, you can print the page of the booklet out and try this yourself. So I'm going to scroll down here. So what I told you at the beginning of class today is I want you to read up to page 10. So if you go here to page 1, let's go to page 1. The author of the book starts talking about those rules. See here? Task number 1. So these are everything that you see from pages 1 to 10 is what the teacher, the person that wrote this book, is saying, and it's very similar to what I'm saying to you. That's okay if it's rule 7. I won't go back and fix it. It's just a rule. But at least that was right. It was 50-50 anyway. Anyway, read pages 1 to 10. You scroll up here. And I'm not trying to skip these on you. I'm just, it's exactly, see, that's the picture, the video that I showed you right there. That was the video. And there's them actually drawing it. But what I want you to go to is page 6. Here's page 6. See? This is the first one that we did. It says, find the radius of the circle. Yeah, page 1 to 10 in chapter 3. Find the radius of the circle that you can fit through these points. Now, I have my workbook from when I was doing this on my own. I tried this as my own work, and you can try it. You should get an answer right here. That's the answer. Try to. Obviously, there will be a little bit of error because of you print the page or whatever, and it's been photocopied. But if you get 123 millimeters on that page, then you did a good job. I'm looking for it in my book right now, so just give me a second, okay? I'm gonna try to share my screen, share my camera, sorry. Yeah, we're starting chapter 4 Friday. So, can you see my screen? There's my lazy attempt at doing it. Okay, I try to do those perpendicular bisectors to the best of my ability. And you can try it on your own too. If you like, I'll take a picture of this. I'll take a picture with my phone, and I'll just put the picture on Blackboard. I'm not testing you on this, so don't. It's a very low stress. It's a very low stress request from me. So I'm not asking you to go and you're not. It's not everything's on the line or something, and you pass or fail because of this picture. Anyway, there's another one for you to try to draw, which is on a future page. It's what we just did right now. Here it is. See? Can you fit a circle in that triangle? That's what I just did with you. That was the one I just did with you, which is the angle bisector. I'm going through my notebook again, and let me share the video, the camera. And you can see it here. I try to fit the circle there. It's pretty good. I measured the radius of the circle, and when I did this one, I was off by 1 millimeter. So I felt very, very, very proud of my work. The other one I was off by 2 millimeters, so I was kind of cheesed about it. But anyway, I blamed it on the photocopier. I don't take responsibility. That's how you gotta be, right? Just kidding. Anyway, when I'm right, it's because I'm right. When I'm wrong, it's not my fault. That's my philosophy. You know what? I couldn't stand when I was a student. I couldn't stand when teachers were like that. If I was lucky. I had good teachers. I'm not gonna lie. I had good teachers when I grew up. When I was growing up. But like sometimes, if you're wrong, it's your fault if it or whatever, whatever I just said. Okay, I'll stop embarrassing myself. Anyway, if you go to the next pages, this is just my lecture notes, so they're a little bit different. But what I've done here is I've just left it blank and I've colored them for you. So you have the green for the special construction and then the blue for the application. So if you want to take these lecture notes will be posted on Blackboard at the end of class. And if you want, you can totally print this out and make up your own question. So what's left in the chapter is very minimal. There is this thing here, which is the triangle inequality on page 11. Now, we actually covered this at the beginning of the course in chapter 1. If you remember in chapter 1, at the very end, there was a question saying, can you make a triangle with 3 sticks? So I already gave you the speech here. So we've already covered this. And I mentioned to you when we get to chapter 3, in other words, today, you would see it again, but I wouldn't cover it because we already covered it. So the triangle inequality with the sticks and whatever. And that leaves us to page 14. Now, the thing is that we're a little bit, let me share the video again. We're a little bit at a crossroads here, people, because I could spend another hour of class, which is what I usually do, talking about naming shapes and focusing on the terminology. Unfortunately, it doesn't really flow very well in the online setting. As I did that with you with the two-dimensional shapes, I realized that I'm showing you names of things and I'm just highlighting words. It's really something more tactile, like you get it in your hands and kind of whatever, right? So I would normally bring shapes to the class and just kind of say, okay, classify them, categorize them, name them. So for that reason, I'm not going to test you on naming shapes. So like you're not going to get a test question on your first test that says name this shape, and then I just like see this thing here, I say name this shape right here or whatever, which is a prism, by the way. So for that reason, I just want you to basically kind of go on your own. I want you to go on your own and read through the rest of the booklet. So we've covered what I want you to really understand in terms of application. And this stuff here, although you won't be tested on it, we are going to revisit naming some of these shapes and just the key ones. But we'll do that when we do surface area and volume calculations, which is many weeks from now. I think 5 or 6 weeks from now, after the break, that is, after the reading week. And when we get to that point, I'll talk about naming some shapes there, and it'll be a much more thoughtful process that way, because what I'll do is I'll give you a shape, we'll name it, and then we'll do some calculations for it. In this chapter, there are no calculations regarding, like, you're not expected to know surface area and volume here. Like, there's no surface area and volume question on your first test. So what I want to end off today's class with is a very, very neat formula, something that you won't necessarily see on the test. You won't see it on the test, but I still want to cover it because it's really cool. Okay? So I'm going to insert a blank slide here and talk about it. Polyhedron. So a polyhedron is the 3D analogy or 3D version of a polygon. You know what a polygon is because you've seen them in your previous chapter. And you know, pentagon and hexagon and heptagon and concave and convex, those are polygons. Here's an example of a polyhedron. This guy right here. Let's just steal it off this page, and we'll dump it into this. We'll dump it into the file there. So let's put that shape in the file here. So this is a polyhedron. There are three characteristics of it that you need to know. 3 names. Those 3 names include vertex or vertices, face or faces, and edge or edges. I'm just writing down the plural because the first one's a little bit awkward. So let's label them on the figure. So a vertice or a vertex for singular is this guy here. So we don't call these corners. These are called vertices. See them? How many vertices does this shape have? How many vertices does this shape have? 4. Okay. And then let's talk about edges in green. How many edges does it have? Let's count them. 1, 2, 3, 4, 5, 6. Good. Now the last one that I want to talk about, which is very important, is face or faces. So what are faces? So a face is the flat surface, and you're right, it is 4. That is correct. There are 4 faces. I'll draw one of them here. I'll just draw this one here because I don't want to, like, if I shade the whole thing and it's going to look really weird. So in terms of the figure, there are 4 faces. So let's give some mathematics to this figure. Vertices or vertex we'll call V, faces is F, and edges is E. So it turns out that it's made of 4 triangles basically, yeah. It turns out that for this, the simplest of all polyhedrons, this formula is always true. That's always true. This is always true, people. Let's confirm that it's true for this one. Let's try to do this one here and see if it works, okay? So for this shape, the left side is what? What's V plus F minus E? Ready? It's 4 plus 4 minus 6. What's 4 plus 4 minus 6? I know you know the answer. I'm not trying to insult anybody here. Isn't that cool? That works for any polyhedron. And if you don't believe me, I will do one more. So I'm not testing you on this, but I do want you to know it because it's pretty damn cool. All right, there it is. How many vertices are there? So how many corners, how many vertices on this figure? 8. How many faces? Think of rolling a die. 6. And how many edges? Think of all the little lines here that make this figure. Let's say you made it out of popsicle sticks. How many sticks do you need to make this figure? How many sticks do you need? Good job. Yeah, you could do it that way, Denny, as well. I didn't want to cheat. So yeah, I'll leave you with one more. Again, this is not on your test, and I do have to dismiss you in a second. Oh, it's a plus sign? Oh yeah, yeah. Anyway, yeah, that would be level expert. This is not really a polyhedron. So it's not flat surfaces, but if they were flat, you could actually use that rule to this one as well. And I'll leave you with that. So we'll start chapter 4 on Friday, and it's going to be applications and the Pythagorean theorem. So anyway, have a good day. I should let you go because you need to get to your next class. Thank you so much, everybody.